What we call scattering in the atmosphere, in our bid to try to explain why we see stars on Earth and not in space, the amusing delusion we have collectively subscribed to actually goes further. It's not diffusion. Science makes the same mistake. Well, science makes the mistake of refusing to believe that radiant energy is what Tesla intended the term to mean. Instead, they claim the opposite, that radiant energy, if you look it up, there's an article on Wikipedia, radiant energy, it's called that. They say it is electromagnetic radiation. So you can see right away we have already socially engineered ourselves to believe that radiant energy is electromagnetism because we qualify electromagnetism with the term electromagnetic radiation. It's like calling the wolf the sheep by saying a wolf sheep. You know, two words instead of one, when we could have just been honest with ourselves and call it a wolf guarding the sheep instead of calling the wolf a sheep by calling it a wolf sheep. It's the same kind of dishonesty, exactly the same. What we call scattering in the atmosphere is actually current traveling in the atmosphere, and that's what we see when the light of the star reaches our eyeball. It is electrons reaching our eyeball as if our eyeball is the other end of a wire. And the pathway the electrons take is that wire of atoms of the atmosphere, atoms of the gas, the oxygen, the hydrogen, the what's in the atmosphere? Nitrogen, oxygen. They make up the wire. In other words, the wire we put in our circuits, made of copper or silver, gold, aluminum, sometimes iron on rare occasions, we choose them because they have the least amount of resistance, but it's still wire. It's a pathway for electromagnetic radiation to pass through because there's very little resistance. Well, the atmosphere doesn't have a whole lot of resistance, but the important thing is they're close together. The atoms of the atmosphere are close enough together so that current can travel and give us this image of a star. Otherwise, we wouldn't see the star at all if it were not for that current reaching our eyeball through the atmosphere. When a lightning bolt strikes, or passes, I should say, through the atmosphere, we know it goes in two stages. There's a preliminary stage of ionization of the atmosphere, causing an ionic channel to form, and then through that ionic channel, the current of the lightning bolt will pass once the ionic channel has been properly prepared and breaks down the resistance, because there's a certain amount of resistance in the atmosphere against a current of lightning to pass through it. So the ionic channel prepares the atmosphere to make it more like a metallic wire in our circuits and less like the insulation that covers the wire in our circuits. So at first the atmosphere doesn't want to behave like a wire, but eventually it does. Now, the reason why it needs that ionic channel and why it's so obvious with a lightning bolt and not with us seeing stars, as I claim the stars are, it's the pathway of current passing through the atmosphere that reaches our eyeball. The reason why is because the voltage difference on either end of that, what's going to be the pathway of current of a lightning bolt, is so great that it's because of that vast difference it sets up its own resistance. In other words, the atmosphere only allows so much to pass through it. And if you're going to leak a tiny amount, then so be it. The atmosphere will allow it because the atmosphere has a certain amount of resistance to the pathway of current passing through it. But if you're going to try to pass a larger amount, it's just not going to happen anytime soon. It's going to continue to leak at a tiny rate, giving us the event we call light. So the only difference between light and electricity is a question of degree. Light is a leakage of current. By comparison to a lightning bolt is a slam, bam, humongous amount of current. But the problem is the resistance of the atmosphere is getting in the way. So the ionic channel has to change the resistance of the atmosphere and reduce it. It has to change the composition of the atmosphere. And this is not the way our circuits work. Our circuits are not dynamically changing their parameters, in this case the parameter of resistance. Usually we build a circuit and it's fixed unless we put a potentiometer in there. So we realize that resistance, the ability to change resistance in a circuit, is a natural feature to electrodynamics. Well, this is exactly the way the atmosphere works. It changes its resistance so that the humongous voltage difference can quickly equalize itself with the passage of a huge amount of current rather than a slow equalization that amounts to what we normally call a leakage, a current leakage. That is what we call light. But lightning is an actual passage of current, just like in our circuit, because now the atmosphere is more like the metallic wire in our circuit and less like the insulation that covers it when the lightning passes through the atmosphere. When you get out into space, the proximity of any stray molecules, floating around in space, what we like to call space dust, they're not close enough together to afford the convenience of current to pass through space. So what we say is, well, there could be a leakage, but it's going to be mighty slow and so faint as to not convey a clear image. It's not going to happen. Relativistically speaking, it's there, but it's so fuzzy and faint that for all intents and purposes, we don't see the stars in space if we were in space. And all that happens is a diffusion. Now we get the diffusion. We get it in space. We don't get it in the atmosphere. We get a diffusion because that's of image, because that's what happens when we get a fuzzy image, right? It expands so that it's not a distinct point in space, a star, a distinct point. It expands and diffuses its intensity of brilliance at that point to incorporate all the area surrounding it so that we can't make out the edge line, the edge that bounds that point. Let's say we were looking at the moon through a telescope. Make it real obvious. Or just we look at the moon in the sky. We see a disk, not a point. And we see it because it has managed to have a boundary condition between the inside of that disk appearance, that apparent disk, and the outside of the boundary, which is non-moon. We don't, it stops, right? And we say that's the horizon of the moon that we're seeing, at the horizon line, because we're seeing it at an angle, right? We're at a distant point. But what it is, it's the boundary condition of the image is what it is. Well, it's distinct, though. If it were to become fuzzy, it would diffuse. It would broaden itself. The intensity of the disk would reduce in proportion to the area, the square area, that continues to broaden and expand as the fuzziness increases. And that would occur if the atmosphere were to suddenly lose its pressure, such that the quantity of air molecules per cubic centimeter, let's say, went downhill and reduced itself. Let's say the atmosphere, let's say the Earth lost its gravity, and the atmosphere decided to leave the Earth and go out into space, because it has a certain temperature, and so that temperature excites now the escape velocity of the atmosphere has been reduced because there's no gravity, and so the temperature of the atmosphere, being a certain heat that we're accustomed to make us comfortable, it causes the atmosphere to have the requisite escape velocity to leave the planet, just by its mere temperature of excitement alone. And so now it diffuses, and it gradually loses the distance, or I should say loses the density, but increases the distance between the air molecules. And so we would see the moon gradually become more and more fuzzy, and because the horizon line of the moon would expand, and the intensity of the light of the moon would proportionally diminish as the moon kept expanding. Now eventually it would become so faint that the backdrop of the sky at night would appear to be no different than before the moon expanded. In other words, it would be the same kind of darkness as before. We wouldn't be able to tell the difference because the boundary line is gone, so we don't get to compare anymore. Now, if the moon were the sun, and we're looking at it through the atmosphere, and the atmosphere is diffusing, going out into space, the sun too would expand its horizon line, expand the diameter of its disk, and in proportion thereto, the intensity of the light reaching our eyeball would diminish to the extent that eventually the sun would fill all of our view, and the intensity would be proportionally less, but it would continue to go down, because remember, the atmosphere is continuing to leave the Earth, and so the horizon line of the sun is stretching out. See, we tend to think that 180 degrees to the right and to the left, of our vision in front of our face is a specific distance. Well, it's not. You know the joke where the man spreads his arms wide apart to say how big a fish he caught, but he's holding his fingers close together because that's actually the distance. Well, the distance between that he's measuring between his arms, if we use that as an indication of how wide is this sun expanding, it goes to infinity, because there is no distance, no limit to the distance that the horizon line of the sun can expand to, which means that the proportional diminishment of the intensity of the light of that sun, there's no limit to how far it can keep dividing down. It's, Zeno's paradox. If you keep halving your distance as you approach a wall, the closer and closer you get, but you never reach it. So now the wall is your asymptotic limit that you never reach. You just keep getting closer and closer. But as you get closer, you reduce your speed to which you move towards the wall. So you never reach it. You just keep slowing your speed. Well, this is the same thing with the sun. As the atmosphere would be diffusing out into space, having lost gravity to hold it here, the sun would continue to diminish in intensity, but at a slower and slower rate as its horizon line expands out to an infinite dimension of breadth, of distance between one side of the horizon line and the diametrical opposite side of the horizon line. But eventually it would reach the point that we would perceive it to be the inky blackness of space, and that's exactly the way space looks from space, is inky black, because there's no atoms to convey light anymore except by way of a teensy-weensy leakage current, so small that you're not going to see anything at that point to speak of. It's going to appear to be black, even though it's not really. So we never get pure black. When we say, those among us who say, you cannot see the stars from space, does not mean that we know what perfect black means in terms of color index. Yet we will all agree, if we were to be out in a space capsule or a high altitude balloon trip, we would all agree that, oh yeah, that's black. That's the color black, the lack of light. But as I'm describing this from a mathematical standpoint and in conjunction with the geometry involved, it's not truly black at all, and it never will be. It can't be, because there is a small amount of leakage current always passing through space. It's just so teensy-weensy that for all intents and purposes we say, well, it's hardly any amount at all. So now a new dominant feature occurs in space that cannot occur on Earth or in our wires, in our circuit for that matter, and that's electrostatics. We get electrostatic pressure building up in the empty dielectrical so-called material of empty space because there becomes a voltage gradient, a voltage difference. That's why we get voltage gradients, because there's no current passing from point A to point B. So we get a buildup of voltage, and that's considered a gradient, which is really a mathematical description of the geometry involved, in which voltage builds up on one side relative to the other side, and we have the gap in between, the dielectrical gap of empty space in between. In this case, because in a circuit we would use glass or mica or rubber or polyethylene or whatever plastic we use as the dielectrical material to insulate our wires or act as the dielectrical material in the middle layer of the sandwich of a capacitor. But out in space, it's empty space that's acting as the dielectrical material, insulating stellar objects from each other to provide a certain amount of leakage current, but for the most part, electrostatic buildup, because the current is so teensy-weensy leakage small that it's not enough to equalize the voltage differences. Now, the transference of information between one voltage buildup point and another is practically just about instantaneous. The analogy Eric Dollard uses is that of a solid bar. If you hold on to the end of a stick and your friend holds the other, the rate, the speed at which you move the bar at your end and the other person receives that movement at the other is practically instantaneous. There's no difference in time lag. There is no time lag to speak of. It's an immediate response. But if you hold a piece of rope and allow a certain amount of slack to occur, and now you have to flick the rope at a tangent, up and down, at a tangent to the direction you want the movement to go, which is away from you and towards your friend, and now you got to wait a time lag for that, what we call an electromagnetic ripple, to pass along that loose rope from you toward your friend. And that takes time. And that's why speed of light has a speed to it. But electrostatics does not. So this is the distinction in space. Now, the necessity to call space the ether in order to explain electrostatic instantaneous communication of electrostatics is totally unnecessary, because it's no different than what's happening inside our capacitor, unless we want to deal with the mathematics involved, because that gets a little more hairy. It turns out that the mathematics suggests an ether without an ether actually being there. It's like a beat frequency. So when we say that scientists are fictionally imagining an ether, That's exactly right, and they have every right to do so. For the same reason that a beat frequency is a mathematical fiction, resulting from two frequencies that cross-interfere and create an undulation of amplitude at a rate of frequency different than the two parent waves, but exactly the same as what should be the beat frequency, mathematically speaking. But now it's a frequency of amplitude as opposed to, well, no, if we're talking about sound waves, two different sound waves that have two different frequencies. The undulation of amplitude of the beat frequency is exactly how a sound wave works within the parent waves. So we have this new sound wave that's the mathematical daughter of the two parent waves, yet it's a fiction. It exists only in our mind because our brain is pattern recognition oriented. It recognizes a pattern of the daughter wave, and yet the daughter wave doesn't exist. We don't get a new sound wave in space. All we have are the two parent waves interacting, creating a beat frequency. Well, it's the same thing with the ether. It's a mathematical fiction that Eric Dollard prefers to call counterspace, involving imaginary numbers, complex numbers made up of imaginary and real numbers mixed together in a complex, in a mathematical complex. And that is the ether. That is where the activity of a dielectric occurs. And the oddity of this mathematical fiction is that the counterspace of this complex realm of a dielectrical material is the opposite of what's going on in space. So if we have the reduction of distance, spatial distance, between the two plates of a capacitor, through counterspace it increases, and it's a reciprocal action. So, just like A divided by B has to always equal the same value, so we reduce the denominator while we increase the numerator, or we diminish the numerator as we increase the denominator. We keep that ratio, well, that's the opposite. You get the picture. You keep the ratio the same. So actually, no, you would diminish the numerator at the same rate that you diminish the denominator in order to keep the ratio the same. Well, but the ratio, is that right? Did I say that right? Well, let's put it this way. Oh, I see what I'm saying. Space is on one side of the equation, and counterspace is, let's say, it's the numerator of the fraction on the other side of the equal sign. That way, it's a hyperbolic function between the two, so that when you increase the spatial distance between two plates of a capacitor, you're actually reducing the counterspatial distance between those 2 points, and vice versa. Okay, now I got it right. I'm trying to visualize this. Obviously, it makes it more difficult. But in any case, so as far as the electrostatic speed limit is concerned, it actually, the rate, the speed of electrostatic communication actually increases the more further apart we separate the two plates of a capacitor, because we make our glass dielectric thicker and thicker and thicker. Now we say the capacitance goes down in farads, so it becomes less and less, but and the geometry of constructing a capacitor of lower farad value means that we create a glass plate, let's say, thicker and thicker and thicker. Yet the counterspatial distance between the two plates is getting less and less, which means that the electrostatic pressure, or I should say the electrostatic speed at which communicates the information that the voltage is changing now on one plate, increases so that it gets to the other plate even faster than before. And what we normally say is that capacitor discharges more quickly because it can't hold the charge as well as a thin dielectric material is the case. See what's happening? But in reality, what it is, it's the mathematical description of the dielectrical speed of electrostatic transmission, so to speak, in counter space is simply being increased. That's what it amounts to. We call it a faster rate of discharge on the opposite side of the dielectric, on the other plate, when in reality that could only happen if the electrostatic flow rate were to be increased. And it is when the distance increases, it travels more quickly. Because it has to, mathematically. It has to work out that way mathematically in order for everything else to work out. So, Eric Dollard is totally correct when he says that longitudinal waves of electrostatic pressure, although he prefers to call it dielectrical waves, dielectrical lines of force, dielectric lines of force, actually surpass the speed of light. Because the speed of light is the speed of current in a wire that has zero resistance, which is a mathematical oddity in itself because there's no such thing. There's always resistance. But that's a mathematically idealistic condition. And then we look for substances to make our wires out of that have the least amount of resistance so that the speed of light is as close to that mathematical ideal as is possible. But when we create a dielectrical material separating two conductive plates of a capacitor, we do the opposite. We're creating insulation to increase resistance, and now what we've done is we've reduced the speed of light, or current for that matter, to a greater and greater degree so that it slows down to a greater and greater extent. And this is the problem that happens when we increase the length of a wire. The resistance goes up. And so the magnetic portion, the magnetism, the magnetic field surrounding the wire of a long oceanic transatlantic telegraph cable, actually the resistance actually goes up and the speed goes down, and that's what happened in the beginning because all they did was use copper for their oceanic cable, telegraph cable, and they didn't realize, as Oliver Heaviside eventually figured out, you got to wrap that cable core with iron ribbon or an iron wire to make it easy for the magnetism to pass through and keep up and not slow down, keep up its pace with the electrostatic portion, the electric field surrounding the copper core, so that the two signals could come out the other end. Well, that's admitting what I'm saying, that if you increase that copper wire, eventually you're going to get a problem with electromagnetic radiation, what Wikipedia calls radiant energy, passing along the length of that copper core to get to the other end. And you're going to need iron wire instead to help the magnetic field get there in time with, in sync with the electrostatic or electric field passing along that copper waveguide of the telegraph, oceanic cable telegraph line, transatlantic, going across the Atlantic Ocean without any repeaters, any booster stations along the way to give it a boost. So this, see, we never really, Krishnamurti said this, we never take our thoughts to their ultimate conclusion. If we bothered to think out the logic of what Oliver Heaviside already figured out more than a century ago, we would already know that we cannot see stars from space, and that we don't need an ether to explain what Tesla called radiant energy, what we call electrostatic, or what Eric Dollard prefers to call the dielectric fraction or portion of electricity. Because it's a mathematical fiction. Anyway, it's all mathematical as it is, but it's empty space that's holding the charge. Now, we know that metallic plate on one side of a capacitor is a high conductor of electricity. We know that. We build it that way. It has very little resistance, yet it's at a tangent to the direction of flow that we want it to pass through. So we put the dielectrical material in its way at right angles to the direction of flow to prevent it from flowing as a current, and instead build up electrostatic pressure of storage within that insulative material. But it's not going to build up in the two metallic plates because they have no resistance. If we look at the metallic plates from at a 90-degree angle to the direction of current flow, instead now we consider, well, what happens within each plate? Well, it's going to equalize, isn't it? Because there's no resistance. So current's going to readily flow around that plate and create pretty much a, what's the word? Homogeneous, a certain amount of homogeneity, not just a statistical homogeneity, but an actual homogeneity of voltage values across that plate. They're going to equalize because there is no voltage. It's all current. They're passing readily. There's no resistance. So it ends up being the same voltage across the entire plate with regard to the other plate on the other side of this imaginary capacitor that I'm drawing in your mind. Well, that plate represents the atmosphere of the Earth, and the current passing through the atmosphere that we call light or lightning, if you prefer, either one, and everything in between. It's all current. It's not diffusion. Not diffusion in the sense that we intend it to be. You know, light is scattering. Yeah, it's scattering, but it's scattering as current. And we are literally electrocuting our eyeball, but to a degree that our eyeball can withstand and enjoy the appearance of the star or the moon that we look up and see, or Venus that we see in the sky. It's like sex. It's a very good analogy. Sex is versus rape or abuse or violence. Violent sex is the difference merely of degree of excitement. Namely, how much excitement will you consider to be pleasurable, and how much will you consider to be violent and stressful and traumatizing. That's the word I'm looking for, traumatic. What's the difference between orgasm and trauma? It's simply a question of degree of excitement. So that if you stay within your parameters of pleasure, then we call it orgasm. But if you go beyond that, now it becomes painfully traumatizing. Yet it's only a question of degree. Well, we don't want a lightning bolt hitting our eyeball, or our skull for that matter. But when we have leakage current, in other words, current to such a minor degree that we can tolerate it, we actually find pleasure looking up at the starry sky and admiring the view, the beautiful view, because we can tolerate that degree of excitement. And anything much greater, we'd go blind. Well, if they did not put a layer of gold in the visors of the helmets of astronauts when they take a walk in space, they'd go blind, because they wouldn't see the sun, for one thing, unless they put a Fresnel lens on their visor to help them see it, because now the Fresnel lens will diffract and cause current to flow through the visor. But the visor is what? Made of glass, let's say. You know, something which is an insulator, a dielectrical material. So it's not going to help them see the sun. It's going to make it even harder to see the sun. So they put a Fresnel lens in that dielectrical material of the visor of the helmet of the astronaut's spacesuit, so that when he steps out of his capsule and takes a walk in space, he can actually see the sun and know where it's located. He can see the stars and know where they are located. But he has to have a layer of gold in that visor to block the sun to a sufficient degree, a very thin layer of gold, to act as a deterrent from going blind, because without the Fresnel lens helping him to know where the sun is located, he would go blind, and without the gold to protect him, he would go blind. So now he can't go blind, plus he knows where the sun is located. He'll look and see, oh, there it is, right there, to my left, or whatever, instead of being oblivious to where the sun is, if the Fresnel lens wasn't there. Or go blind if the gold layer in his visor was not there. Well, they have to do the same thing with the windows on the space capsule. They'd go blind if they looked at the sun without the gold there, or they wouldn't even know where the sun is located to orient themselves. If they have to orient the space capsule, where's the sun? Where's the Earth? Where's the various stars, the stronger ones that I'm looking for to help me guide my space capsule in the correct direction? Well, if you can't see them, you're not going to be able to guide the space capsule. So you got to have a Fresnel lens, and you got to have a layer of gold there in case the sun should come through the window and strike your eyeballs so you don't go blind. You have to create an artificial atmosphere in that glass, because the glass is a dielectric, so it's not going to respond properly like an atmosphere will. So you have to artificially create it in your construction of the glass window. If it's glass that is the window, let's say, I'm just supposing for the moment, for argument's sake, you have to structure its geometry and its composition of materials to function the same way the atmosphere does. Protect your eyeball on the one hand, but allow you to see the stars and the sun and the moon and Venus on the other hand as well. Both conditions have to be met in constructing that window, or the visor on their helmet, that the atmosphere qualifies. So these are the things that we don't bother to take the trouble to think through. Yet if we use that analogy of Oliver Heaviside's mathematically solving the problem with his telegraph equation, the problem of how to construct the transoceanic Atlantic cable, telegraph cable, we never would have had the ability to figure out for ourselves, if we bothered to take the trouble to think it through, the consequences of that telegrapher's equation, that we cannot possibly see the stars, or anything else for that matter, luminous, from the vantage point of space. We can only see it from the vantage point of standing down here at a certain elevation on the planet Earth. Because if we went too high up, such as high altitude balloonists will do on occasion, they will not see stars in space. It'll be inky black. Something slightly less than black, obviously, as I've already discussed, but pretty black nonetheless. Close enough to be considered black and recognized as the color black, or the colorlessness of blackness. So now I've covered all the main points, and now you can see just by argument, we already have the knowledge. This is why I keep saying science already has the knowledge of how the universe is actually constructed, but we don't even bother to take the trouble to integrate by taking everything to their natural conclusion, their logical conclusion, to come to the same conclusions that some people have expressed, such as Peter Lindemann on a YouTube video. Somebody videotaped him at a conference during the break, and he says you cannot see the stars from space. And Thomas Brown went and interviewed some of the astronauts, or at least one of them, and he admitted in the early days of the Gemini or Mercury program, I forget which came first, they didn't see the stars, and they had to learn the hard way. They had to construct the windows of the space capsule a certain way, because they'd either go blind or they'd never see the stars in the first place. For that matter, either one, both, and, not or, and. If they didn't know any better and just put plain glass there on the windows of the space capsule, as they did their orbital pass around the Earth a few times and then come back to Earth. They never asked the monkeys, but see, that's it. They probably did learn from the chimpanzees or whatever, the rhesus monkeys they sent up in space. The rhesus monkeys went blind. If they bothered to check their vision, I don't know. I can't remember how that works. Anyway, They might have had visors. They might have had blinders on the rhesus monkey's face, for all we know, so they wouldn't touch anything. And I don't know. I don't know. That's an interesting question. How come we waited till the humans were sent up? How come we didn't know ahead of the humans that the rhesus monkeys went blind by the time they got here? Well, maybe they had never had the opportunity to look at the sun, or stare at it, for that matter. I don't know. I guess if well, you know, animals have a greater intuitive sense than we do, so maybe they had the good sense to close their eyes when the sun was shining through the glass window and hitting their face. I don't know. I don't know the answer to that. It's interesting. You know, you solve some problems, and then other questions come up. So, you know, knowledge is an endless affair, right? We'll never know everything. We just keep learning new things, but then we realize new questions as we answered the former ones. Now we got new ones to answer, and so we don't. That's a question I'll have to leave open. How come we didn't learn sooner, before we sent up humans, that this condition of space is the true condition that occurs, and not what we're told in popular media? So that, I think, covers why I say there is no ether, because it's a mathematical fiction. It exists mathematically, but it doesn't have to exist in actuality in order to explain the mechanics of the universe. It's enough to say it's a mathematical reality, because it is a mathematical reality, just like beat frequencies are a mathematical reality. So is the ether. So is the ether.